Right. We are still doing the shear force. Now let's take the first example. After recapping that whenever a beam is loaded, the beam will always be subjected by the twin effect of load. We have the shearing effect and the bending effect. Now, how do we quantify that? It's by drawing the shear force and the bending moment diagrams. And the shear force, as we've said it before, it is that force that acts on the cross section of a beam, trying to shear off the spans of the beam, trying to make one portion of the beam by cutting off, sliding over the other one. The bending moment is just the fact that the load is having a tendency to bend the beam to create an excessive deflection that can bring a failure. Now, how do we quantify those two effects? It's by, as I've said, by drawing the free body diagram. Now we have a simple case here of a simply supported beam with two loads. One load 10 kilonewtons, another one 10 kilonewtons. We have different distances from different point loads. Here we're just dealing with point load. Now the very first thing that we need to do, what is first of all requested here? We are requested to draw the shear force diagram and the bending moment diagram. And it's very important, as we're repeating, we need to know the definition of what does it mean when we're talking about shear force and bending moment. By repeating, we say the shear force is the effect, is the failure due to the shearing off of the beam through the load. The bending moment is the failure that creates bending, excessive bending of the moment due to the load. The load can be live load or distributed load, UVL or UDL. And how do we know that this section of the beam will be exposed to a very high or small shear force or very high or small bending moment? Is by drawing the bending moment and the shear force diagram. Therefore, this section is very important because although we know that the beam will be in equilibrium, but we need to know what sections of the beam might be subjected to a shear effect or to the bending effect. Because failure of beams will always take place through shear effect or shearing off of the beam, or through bending effect, or through the deflection, excessive deflection of the beam, which is normally the bending. Now, in this case, this is what we are given. This is the beam loaded in C and D with point load and a simply supported beam, as you can see. Here, the very first thing we need to do, the very first thing to do is to calculate the support reactions. Here already we got the values, and we know how to get these values by using the equation of moment about B will give us the reaction on A. The moment, the sum of moment about A will generate the reaction at B. Everybody knows how to get the reactions, and calculating reactions are very critical, because if you make a mistake by calculating wrongly the reactions, even your shear force and bending moment diagrams will be wrong, totally wrong. Then we need to be able to calculate exactly or precisely the reactions, because that's the beginning. Now let's start with the shear force. How do we draw the shear force diagram? This is the zero line. We call this zero line. As I've said, the shear force will be the sum, algebraic sum at the left and right. If we look at the point load, now we can start at A or we can start at B and come in this side, or this side going the other side. But let's start with B. Now the shear force, we need to do the shear force at A left. What we have at the left of A there is no load. Therefore, the shear force at the left of A is 0. Remember that the shear force has an impact at left and right. If you look at this load F1 and this load F2, when this load F1 is acting on point C here, obviously we'll agree that this load will have an influence here at the left, and it will also going to influence the right side of the span. Now, if we have a reaction, we'll have to look at the left side of the reaction and the right side, and we'll move point after point because the shearing effect and the bending effect are likely taking place on the point load, but affecting the right and the left side, especially for the shearing effect. The moment will be taken on the point because the moment takes place. When we're dealing with a moment, we know that we need to have a pivot. We need to have a point of application of a force. We need to have a pivot and to see how the object is being affected by the rotative effect of the force, or in this case, the bending effect of the force. Now, left of A, it's 0, as we can see. There's nothing here. It means even if there's a reaction here, which is a load acting to the influence of an action, a reaction can be taken as a load. We can consider it as a load because it's acting due to the action of the load. At the left of A, there's nothing. At the left, the right of A, what do we see at the right of A? Defining a shear force as an algebraic sum, we take ourselves at the right of A and we look at what is remaining. How many forces do we have if we are in this span AC? The only force we have is the reaction. We are done with point A. We've taken left and right. Now we move to C. Left of C. You will see that the left of C is the same with the right of A. What is the left of C? This is C. I put my hand on C, and what is remaining on the left of C? Everybody will see that it's the reaction. And we've already calculated the reactions. Everybody knows how to calculate the reaction. We've already calculated them, and everybody should be able to do it properly. Now, C left, this is C, and the left of C, how many forces are remaining? The algebraic sum of forces that are remaining is just only force, if we look at the left of C. The right of C, we are in this zone, and what is remaining at the left? Because if we're looking at the right of C, the impact of the forces that can shear off the beam are these two. And as you can see, we have the reaction that goes up, C right, we have the reaction that is toward positive values of Y, to be positive, minus, here we take the algebraic sum as we said, then it means minus F1, RA minus F1. RA is 8, F1 is 10, this will be minus 2. You'll have to plot the values after. Then we go to C, we're done with C, left and right. C, no, now it's D. D left. You see that the D is here, the left will be the same with the right of C, which is RA minus F1. F1 being 10, RA being 8. This will be minus 2. D right. We're taking left and right by definition of the shear force, and by the impact of shear force, it's always having an impact in the left and the right of the load. D right, we are here now. This is the right of D in this zone, and the remaining forces, if we do this algebraic sum, it will be RA minus F1 minus F2. means minus F1 minus F2 is minus 20. 8 plus minus 20 is minus 12. Then we go to B left. B left will be the same than the previous. B, the left of B is here, and the remaining will be the same. The equation will be the same. And the value of the shear force will be minus 12. Then shear force at B right. We are now here. What remains is all this. It means we have the sum of reactions and the sum of loads. This should, if our reactions are properly calculated, we should have 0. It means we'll have RA minus F1 minus F2 plus RB. RA being 8, RB being 12, these two, 10, 10, 20 minus 20 will be equal to 0. Now, if your reactions are calculated accurately, you should start with 0. If at the left there was no load, because this is a simply supported beam, but if you had an overhanging beam with a load here, this can't be 0. Well, it could be 0, depending, but if we started with 0, we have to close with 0, logically. Now, let's draw the shear force diagram itself based on the values that we have here. We have our 0 line here, and this is A left. A left is the starting point, 0. A right, we're still on A, then it means we're still on A. We have 8 here. We take 8 and then join this. We're done with these two. Now we're going to C, left and right. We are here. C left is 8. We are on C. Again, 8, because this is a 0 line. We call this our 0 line. Everything is taken from the line to the value. If this is 0, 8 is here. 0 on C, 8 is here. But C, we have the C left and the C right, minus 2. It means we need to go below the 0 line. Minus 2, let's assume that is here. Then we'll join, first of all, the point and have something like this. C right. We are at C. A is A left, A right, C left, C right. That's minus 2. D, the next is D left. We're already on D. D left is also minus 2. 0 line, minus 2 is here. We can join the previous one with the new one. That's D left. D right, we're still on D. This is the section D. On the section D, we have minus 2 and minus 12. Minus 2 was already taken. Minus 12 could be somewhere here. Join it as well. We're done with the D. Then we're going to B. B left, minus 12 as well. This is B, minus 12. We'll join it with the previous point. And we're done. And then 0. We got back to the 0 line. And this is our shear force. If we can reinforce it. Our shear force diagram. As you can see, we can easily read which section of the beam might have the biggest shear force. I think we can see that the biggest shear force should be, I think, this one or this one. I don't know. Should be this one, because this is 12 units and this is 10 units. This is also 10 units. It means this is where we have the biggest shear force. But the sign, whatever is above the zero line will be given positive sign, and anything that is below the zero line will be given the negative sign. We are done with the shear force diagram. And always remember, the point where the shear force is crossing the zero line will correspond with the bending moment maximum. It means when we draw the bending moment maximum, we'll see that in this section, that's where we'll have the biggest bending moment. Now let's draw the bending moment diagram. Zero line as well for the bending moment diagram. Now here, how do we proceed? Bending moment diagram is a moment, and we know that a moment is always defined by the force times the perpendicular distance. And here, how do we proceed? Whenever we talk about a moment, we need to have a pivot. It means we'll be taking each point where there's a load as a temporary pivot. Now let's start with at point A. If we look at point A, what do we have on point A? Everybody can see we have the reaction RA and the pivot A. Therefore, the bending moment at A, what is it going to be? Because the load is acting on the pivot, what are we going to have? The load on the pivot will create a moment which is 0. Point B. Point B. What do we have on point B? This free body diagram will tell us like this is what we have. We have the beam. We have, first of all, not the beam, but we have the reaction. And at point B, not B, sorry, it's C. The next one, yeah. We have F1. F1 is acting at C. And this is the free body diagram of the situation that we have. Therefore, the bending moment at C, what is it going to be? C being our new pivot. The previous pivot was A, and there was only the reaction on the pivot, and the bending moment at that point was 0. Now we're moving to C. What are we going to have? To C, we have F1, which is on the pivot, but we have RA that creates a moment about the pivot. And this moment will be RA times the moment arm, which is 2. F1 doesn't create a moment on C. And therefore, the bending moment at C will be RA times 2, which is 16 kilonewtons meters. Let's move to another point. Remember, because it's a bending moment, which is a moment, moment can only be about a point. And if we're calculating the moment about a point, we do it by calculating the algebraic sum of the moment for the forces that are left behind. If we are at C, how many forces are left behind? We have the reaction. The reaction will create, obviously, a reaction. A bending, a moment. Now, if we move to D, point D, we can see the free body diagram. If we are at point D, we'll have something like this. At D, that way we have F2. We still have at the left the reaction. We still have F1 at C, and our new pivot is D. The first pivot was A, and we only have one force on A, which is the reaction, and the moment was 0. We move to the next pivot, which is C, and at the pivot C, it's only RA that creates a moment because F1 is on the pivot. When we move to the next pivot, which is D, we can see that all these forces will create a resultant moment at D. And what's going to be the BM at D? The value of BM at D will be RA times the moment arm to D. What is the moment arm? Is 4. RA times 4. And the moment, as you can see, it's clockwise. F1 will create an anti-clockwise moment minus F1 times the moment arm is 2. And we can get the resultant moment at D, which means 8 times 4 minus 20, 32 minus 20 is 12 kilonewtons meters. That's the moment on D. We started with 0, 16, 12. Now, what is the next point? And the last one is B. Point B. B becomes our pivot, and all these forces will create moment. RA will create the moment, and the moment arm will be 5, 2 plus 2 plus 1. F1 will create an anti-clockwise moment times the moment arm, which is 3. F2 will create an anti-clockwise moment with the moment arm, which is 1. Then RA times 5, which will be 8 times 5, which is 40. 10 times 3, which is 30, minus 10, and this will give us 0. We can see that whenever our reactions are well calculated, even at the last support, the moment should be equal to 0. Then we'll plot these values on our diagram. Now we have a choice when it comes to the bending moment diagram. Generally, the positive values will always be below 0, not below 0, above 0, mathematically speaking. But in a practical way, as you can see, when these loads are applied, they have a tendency of creating this type of bending. Therefore, it's always advised to put the bending diagram, the positive values, below 0, but you can still put them above the 0 line. It's also fine. But if you put them below the 0 line, you need to specify that your value below the 0 line are representing the positive values. Now, the first value was at A, the moment was 0. At C, it was 16. If we want to take the top, 16 might be, let's take 16 here. Then the next one was 12 kilonewtons meters, all of them, they are moment. We just plot them below or above, and the other one was 0. If I put them above, and I will join them by straight line, because we have point load. It should be straight line, strictly straight lines. Or else, if I take my positive as below 0 line, it will be something like this. Then in that case, I will have to put the sign. We have a choice, but most of the books, they prefer putting the bending moment diagram positive below 0 because it reflects what takes place, and you can easily read where do we have, and as I've said, it's at the point where the shear force crosses the 0 line, On that point, that's where you have the biggest moment, the maximum bending moment. You can see this is the maximum bending moment, which is 16. Because we have the 16 here, we have the 12, and we have 0. And the point, if in case the bending moment was crossing the 0 line, the point where there's a change, or the change from the positive to the negative value for the bending moment diagram, is called the point of contraflexion. But in this case, we don't have the point of contraflexion because nothing is crossing the 0 line. And as I've said, we have a choice either to put mathematically correct the bending moment diagram by putting everything on top of or above 0 line, or practically correct by putting everything below 0 line and put the signs. This is the first case where we have only point load. We will take different cases as we're progressing with distributed load, with applied moment, and see how the shear force and bending moment diagrams can be represented. But to recap, what we need to remember very well is the definition of the shear force and the bending moment. Why are we doing it? It's because whenever a beam is loaded, we need to be aware of the fact that the failure can take place by two ways. We call it the punishment or the twin effect. Or the way failures takes place will be either by shearing off the beam, which is taking place at the cross section, by cutting off the beam and trying to slide the spans of the beam one over each other, or else by bending the beam, and the beam will take a deflection, and if that deflection is excessive, the failure can take place. Now, to quantify the shear force and the bending moment, the shear force and the bending moment, we can do it via the diagrams, because the diagrams can allow us to read. As you can see, I've showed you from the shear force diagram, you can see which section of the beam is likely to be sheared off and which point of the beam is subjected to bending moment maximum, meaning that the section on which, if there's an excessive bending, the failure will take place on that point. We will carry on with other cases in the next session.